All right, so we started this series of videos with this exact diagram, and I told you sort of preemptively that this is where we were going to get to. But we needed to sort of reaffirm to ourselves that we understood how different species manifest, specifically different acid or base species manifest at different pHs inside an acid-base system, especially for polyprotic acids. And so what we know is for something like H2A, that can dissociate to HA minus plus a proton, which can then further dissociate to, well, just say proton plus A2 minus. And we know now really well that that first equilibrium is dictated by that first equilibrium constant, pKa1, and the second dictated by pKa2. We know that when the pH of the solution is equal to pKa1, that's when we have equal concentrations of H2A and HA minus. And then we know that when the solution is at pH equal to pKa2, that's when we have equal compositions of HA minus and A2 minus. And that we know that when the pH is below pKa1, then our dominant species is going to be H2A. And when it's in the middle of the pKa's, our dominant species is going to be HA minus. And then when it's in excess of pKa2, our dominant species is going to be A2 minus. That's what we learned. We call that process speciation. It allows us to determine what the dominant species is at any given time. And the cool part is that this fractional diagram is just a summary of exactly that, except we can compute pretty quickly instead of having to go through Henderson-Hasselbalch equation and ice tables and compute. If we have an alpha diagram already available to us, then each point is already computed as a function of pH for all the species. And so essentially, what these are systematic treatment of equilibria at every single point as a function of pH. So it saves us an enormous amount of time. They're also really illustrative because they're nice and highly symmetric like this. They really, to me, help me understand speciation in a way that simply doing the math doesn't. So in a fractional composition diagram, old school textbooks will call these alpha diagrams because the fractional composition is denoted as alpha. That's what you see here in the labels, alpha of each of these species. The y-axis or the ordinate axis here is alpha. It's the fractional composition from 0 to 1. What percentage of the solution is that particular species? At any moment in time, that at a given pH, the alphas of the three possible species here will add up to 1. And then, of course, all of this is a functional of pH. For this, this acid, this is fumaric acid, we've got these two pKa's here. And so what we know is that at very low pH, our dominant species is going to be the H2A form, right? And that's why we have 100% at pH 0. And that as we progress, what we're doing is starting to push the equilibrium in this direction. And as we push the equilibrium in that direction, we start to grow in this HA species until these two curves intersect, and they intersect nicely at that first pKa1. That's when the two species are equal to each other, when the pH is equal to the pKa. As we continue past that point, now the H2A becomes a minor species in solution, meaning it's no longer dominant, and HA is dominant, and HA becomes dominant at roughly half of the pKa1 plus pKa2. That's when that species is at its maximum. And then beyond that, we start to shift towards the last species, the A2 minus, the dibasic species, till we intersect those two curves at pKa2. That's when the fractional composition is half for each of those, which means that the concentrations are equal. And then as we push further past the pH of 4.48, we're left with a species that's dominantly A2 minus. We can make these curves not simply for acids and bases. We can make this for any speciating system, but for specifically when we talk about acids and bases, they become really helpful in helping us understand what's in solution at a given moment in time. And so the next chapter, we're going to introduce titration curves. These are really helpful in helping us understand titration curves. We can use these to essentially derive a titration curve, or we can use a titration curve to essentially derive one of these things. Just to reiterate, the alpha here is the fraction of the entire solution that that particular species comprises. And so we could write that out as alpha is going to be equal to whatever that. So maybe this is H2A. So it would be the concentration of H2A divided by what we consider to be the formal concentration. Again, the formal concentration is whatever the original concentration of the thing that you put into the system, and since they're all connected to each other by equilibria, the formal concentration really constitutes the concentration of H2A plus the concentration of HA minus plus the concentration of A2 minus. That's what formal concentration means here. And so the fraction is just what percent or what amount is in that form. And we can do that for any one of these. There are some nice derived methodologies to compute the alpha directly, because in order to compute the alpha in this form, we would need to go through all of the equilibria first, compute the concentrations of each species, and then compute alpha. You can do it that way, totally, but I'm going to show you some shortcuts to that as well. So the alpha equations, if we didn't want to do it through just general equilibria, which takes a little bit longer and more cumbersome, they differ depending on how many protons you have in your system. So there's going to be a set for monoprotic, diprotic, and triprotic. I'm going to derive the monoprotic system just for kicks. I'll never ask you to derive it, just so you see where it's coming from. You can always refer to this video. And then I'm not going to derive the other ones, though you can see them in my notes if you want. I'm just going to give them to you because they're useful to use. They're not really useful to know where they come from. So to derive this, we're going to need a couple things. We're going to need the normal equilibrium expression just for the dissociation of HA, which I have here. That's the first step, which we know we've got that down pat. Second one is a mass balance equation, which we just talked about, where the formal concentration, or whatever the original concentration of HA that you add to solution, some amount of HA is going to dissociate. So that formal concentration has to be the total of the two, A minus and HA, because some amount's going to dissociate X, and some amount HA minus X is going to be left in solution. So taken together, that's what we have. I'll also note that a lot of times I write F, and you can see this in my PDF where I do the derivations. I write this as HA naught or 0, because that's the initial concentration of. So I use that interchangeably, just so you know that. So we're going to start by determining what the alpha equation or expression would be, meaning the expression that would allow us to compute the fraction of HA in solution at any given pH. Okay, so first step is just combining those two, the two expressions that I have above. So what I did was took the mass balance expression and solved it for A minus, which would just be F minus HA. And then I substituted that in for the A minus part here on the Ka expression. So really that's all that changed, is now you have F minus HA instead of the A minus, simply from substituting the mass balance expression. Now I just need to distribute that numerator, so I've got the H plus, I'm going to distribute into the F minus HA. That's what I get next. Now multiply both sides by HA to clear out the denominator, and I get this new expression. Okay, now I'm just going to move both of the terms with HA in them to the left side of the equation, which is what I get here. So I've got this term and this term equal to H plus F. Now that I have two terms with HA in them, I'm going to pull that out, and that's going to give me HA, and then the parenthesis term Ka plus H plus is still equal to H plus times the formal concentration. Okay, so finally just solve for HA there, and we get proton concentration times formal concentration over Ka plus proton concentration. We're not done yet. That's just the concentration. Remember, we're trying to get to the fraction of the concentration at any given pH. So we want that fraction as a function of the hydrogen ion concentration. So remember, from the definition of alpha, that's the fraction of HA in the solution at any given moment in time, as a function of pH. So that's going to be the concentration of HA at that time divided by the formal concentration. So that's the sum of all the different possible species. So what we can do is just take this HA that we just computed in terms of H plus and formal concentration, so in terms of constants and pH, and we can substitute it in for the definition of alpha. So that gives me this big clunky equation, but we can get rid of some stuff. So you know, the way that this is written is kind of misleading, but this is really a fraction over a fraction. So we have formal concentration by itself in both numerators. So we could get rid of the formal concentrations. And that gives us our expression for alpha, for HA. That gives us proton concentration over Ka plus proton concentration. So note that in this case, for us to be able to compute what fraction HA exists in solution, this is pretty nice, right? This is pretty convenient. I don't have to go through the whole equilibrium, to have a nice table, solve for everything. Instead, what I can do is simply, as long as I know the pH of the system, which might be something you don't know, but if you do know the pH of the system, which you often do empirically because you can measure it really easily, then you know the fraction automatically, because the rest is just a constant. Because the Ka you can look up in a book, you can measure this as pH, and now you know the fraction of your species in solution. So it's a really nice tool. This is also how the alpha diagrams are calculated that I showed you before. So I'm not going to walk you through the derivation. It's actually not that hard once we know the HA, but I'll just give them to you, and this is what I'll always do in this class. So I'll give you these because I never want you to memorize them, nor do I really care if you know how they're derived. I just didn't want you to think that it was coming out of nowhere. So the fraction of the conjugate base then is going to be Ka over proton concentration plus Ka. So these are the two key alphas for a monoprotic. So of course there's a general form to this expression for HNA being the number of protons in a polyprotic system. And so if you want to compute what the alpha is for that fully protonated system, that's just going to be proton concentration squared over D, and I'll show you what D is here in a second. And for any subsequent species, it's going to be its K value times the concentration of protons n-1 over D. D here is this series where you have proton concentration to the n plus the first K times concentration protons to the n-1, then K1, K2 proton concentration to the n-2, K1, K2, K3 proton concentration n-3 up through Kn. So that D goes in for each of the denominators here. So this is kind of a good spreadsheet problem. It's cumbersome if you've got a triprotic or a tetraprotic acid, but it's more convenient than having to go through the systems of equations to solve them using just a normal approximation in solving the equilibrium expressions. So getting the alphas is still going to be the faster way, especially if you can do it in a spreadsheet.